Live from Laverne, this is the past talking to you as Grandmaster C speaks to the future. Chapter 16, C, about acids and bases. But then, I am also the Cringe Master! Woo! All right. Last part of chapter 16, guys. And here it is, 16C. Cringe Master C here. Mr. Canu has asked me to fill in for him, and GMC has been doing his part, and my Star Wars friend Trev Lucas Spa Woo has also been doing his part. So we're helping him out at a time like this. So, what are our objectives? We've talked about the idea of what acids and bases are. Okay, how do they behave? We've talked about strong acids and weak acids, strong and weak acids, strong and weak bases. And that we know that's nothing to do with concentration, has everything to do with how well do they dissolve in water. Then we talked about the idea of the pH scale, okay? And we're probably going to do a separate video covering the pH scale, because that certainly can be an involved little thing. So let's get to the last part of chapter 16. Objectives. Student will be able to understand that acids and bases neutralize each other and form salts. Right, they cancel each other out. Now, student will be able to understand that titrations are a way to compare an unknown acid or base using an indicator to tell when neutralization has taken place. Titration is one of the most important things that can be done in chemistry when we are looking at the pH of an unknown acid or an unknown base, when we test it against something that we know the concentration of. Student will be able to understand that buffers slow down the rate of change in the pH of a solution. Yeah, let's do it. All righty. So this is a pretty important idea when we look at neutralization, okay? And if we've got a pH of 1 acid and a pH 13 base, and we combine it, they cancel each other out, and we get a pH of 7, which is neutral. Even though it's neutral, personally, I still wouldn't drink it, okay? There are smart choices out there to be had, okay? Salts. This is where I've got to clear something up with you guys. In the world of chemistry, salts, it is a very big, wide term. It's what I call an umbrella word. Kind of like cars. When we say cars, well, wait, Cringe Master, what are you talking about for cars? Well, like God's own Ford 67 Mustang, for example. Chevy Camaro. How about a Chevy Nova? Toyota Paseo, Toyota Corolla, Lamborghini Countach. Oh yeah. All those are cars. Now, there are different kinds of cars, but they all fit under the category of cars or automobiles, if you want to use that. Salts in chemistry, it is another umbrella term. Most people out there think of sodium chloride. Well, typically, that's the salt that's used at the table in cooking, make the food taste better. If you are dealing with a heart patient who is on a sodium-restricted diet, but they can have salt substitute, it's called potassium chloride. Okay, that's another kind of salt out there. Now, is there a difference between the potassium and sodium chloride? Actually, yeah, there is. They're both salt. They don't quite taste the same kind of salt. I'm not saying one is more salty than the other. It's just that it's different salty, if that's the best way to look at it. Just like in sugar, you've got table sugar, you've got fruit sugar, right? They both taste sweet, but they don't taste exactly the same. Now, let's pull back here for a moment. Salts. They're formed when the anion, think negative the negative part of a molecule of an acid, and the cation, that's the plus, of a base combine. And that is produced by neutralization reactions. Yep. So let's take a look here for an example. Here's a classic. We have sodium hydroxide plus hydrochloric acid gets us water plus sodium chloride. Water and salt. Yep. So we can actually take drain opener, sodium hydroxide, and stomach acid, combine them, we would get water and salt. Now, again, would the Cringe Master, Grandmaster C, Trev Lucas, Spa Woo, Disney killed Star Wars, tell you, hey, it's safe to drink that because it's just water and salt? I wouldn't. No. And neither would Trev Luca. Neither would Grandmaster C. And certainly not Mr. Canu. He wouldn't be telling you those things either. But nonetheless, they do cancel each other out. So the salt is formed when the negative part of the acid hooks up with the cation of the base. Okay? And that's kind of it. Now, what do you mean? What are you talking about here? Well, here's NaOH. Well, what's given up? Okay? Well, what's given up? The sodium drops the sodium hydroxide drops out the atom. The hydrochloric acid drops out the H. They kind of swap. Okay, so you got H2O, and then here you got NaCl. Okay, so this is what happens. This is the salt. The anion of the acid, which is the Cl, because that's a -1, combines with the cation of the base, Na+. But wait, Canu, you told us you're like 2 videos ago, I'm not Canu, I'm Cringe Master. Yo, I'm sorry, Cringe Master. You told us earlier that it's all about the hydrogens. Protons, me boy, protons. Or, I should be specific, cations. I gave you a quick and dirty definition of that, where it's protons. But the reality is, it can be cations. Okay? And that's just the way that it is. Okay, what do we have next? So that's produced by neutralization reactions. So when we look at titrations, these are controlled neutralization reactions that are used to determine the unknown concentration of a solution. Now, we can look at a titration curve. If we were to go and put the pH, and we're looking at an unknown acid, okay? And here we have a volume of NaOH, okay, that we're adding. So let's say we start here, down here at the bottom. Okay, you'd say, well, look at the pH. Oh, it's a pH of 1. Yeah, that's a concentrated acid. That's to be sure, man, because, anything below a 7 on the pH is an acid. All right. So what we do is start adding a little bit of the NaOH. So we're adding a base that we already know what the concentration is, because we don't know how concentrated the acid is. I mean, we have a pH, yeah, but we need to know molar concentration. That's what we really need to know. We got to guess kind of with the pH, but we got to be more precise for it. So we're adding the NaOH, and you kind of notice the red dots. That's when we've been adding more and more, and that's when we stop to check to see, has it reached a neutralization point? And that's it right here. You can see, oh, look, you got this dot here, and then you got the remaining dots over here. So if you look at this curve, this thing is slowly going up, and then all of a sudden, it just shoots up. Okay, shoots up like a rocket. It's shooting up like Grandmaster C next album release sales. Okay, shooting up there so fast in such a short amount of milliliters of NaOH. And then the rest of it, we don't care. So what are we interested in? We're interested in this middle part here, because this is telling us how much base do we need to add to the acid to neutralize it, to make it a pH of 7. That's the whole idea behind an acid-base titration. Okay, so when we look here, we have a titration of 100 milliliters of 0.5 molar HCl. Half a molar of HCl, okay. So that means if we had 1 liter of this stuff, we'd have half a mole in it. Okay. Down here, we have milliliters of 1.00 molar NaOH. So if I have 1 liter of that NaOH, I have 1 mole of NaOH. Okay. So let's go ahead and we can use something called indicators. Okay, indicators will turn color in the presence of a certain pH, and that helps us. It helps us tell when did we reach that point. Now there is something called the end point. There is something called the equivalence point. All right, but if you notice right here, it ends right here, the equivalence point, pH is 7. That means the acid and base have canceled out. Now it's a pH of 7, and it requires 50 milliliters of 1 molar NaOH. Now, we started out with 100 milliliters of half a molar of HCl. So if we look at it, the NaOH is double the concentration of the HCl. So if you have 100 milliliters of 0.5 molar HCl, then it's reasonable to assume that if the NaOH is double that concentration, it only needs half of that 100 milliliters to cancel it out, to reach that equivalence point. Okay? And that's it right there. So that's when you notice, hey, 50 milliliters of 1.0 molar NaOH. Oh, wow. Wow. Exactly. It's not that hard. It really isn't. Now I'm working on trying to find an online simulation for that. So, equivalence point. The equivalence point is equal moles of acid and base, whereas the end point is the color changes at pH of 7.0. Can they be the same? Yes. Are they always the same? No. Wait, what? Let me explain. Think back. Earlier in the chapter, we talked about strong acid, weak acid, strong base, weak base. Remember? And we were not talking about how concentrated they were. We were talking about how well did they dissolve in water. Okay? So weak acid, weak base, maybe 5% dissolves in the water. Whereas the strong acid, strong base, all of it dissolves. About 100%. So that equivalence point and end point, if it's strong acid, strong base, weak acid, weak base, that's going to work, where the equivalence point will be the same as the end point. Okay? On the other side of the coin, if you have a strong acid, weak base, then it's a different number, and I'm not going to worry about that here. I just want you guys to realize that there is a difference when you look at strong versus weak in a titration. Strong, strong, weak, weak, that works fine. But when it's strong versus weak, the equivalence point and the end point will not be the same. Okay, is there an easy, quick way for us to figure this out? A quick formula for us? Absolutely. The equation used to solve for the unknown molarity concentrations, it's M, the molarity of K, times the volume of K, equals the molarity of U times the volume of U. Huh? Why? In other words, if we're talking about the equivalence point, it's equal moles of acid and base, right? So therefore, the number of moles must be the same in order to cancel each other out. Okay? So when we look at our formula of molarity is equal to moles divided by volume, moles over liters, right? If you multiply the molarity times the volume, you are left with moles. That would be your answer. So when we look at this, molarity of the acid times the volume of the acid is equal to the molarity of the base times the volume of the base. Boom. That's what we have. Okay, so spend a little more time working on that. Our last part, buffers. You may have heard of something called buffering. When aspirin first came out, it was a nice pain reliever. It was good at thinning the blood. Okay. If old people have a heart attack, they can take a couple of the baby aspirin and that will help, but they still need to go to the hospital. Okay. But one of the problems about aspirin, it's made up of salicylic acid. Okay. Now, I want to point out something. Is that the same thing as, the illegal drug? No, it's not. There's many different kinds of acids out there, okay? So you have to understand, acid is another umbrella term, just like base is an umbrella term, okay? Just like salt, that's an umbrella term, okay? Buffers, because when people were taking aspirin, they would complain about their stomachs hurting because of that acid. So a company added a coating of buffered material around the pill, okay, the aspirin, that when people took it, excuse me, the stomach would digest the buffered part, then it would digest the acid, and people could take it without a problem. So that's the idea behind a buffer. It's a solution that resists changes in the pH. And again, it's most effective at regulating slight pH changes. And there you go. Hey, there's going to be a couple of other videos out there, but at this point, we are done officially with Chapter 16. Woo, woo! Okay? And I'm not cracking any dad jokes at this point. But this is it for Chapter 16. I hope you guys benefited from it. And this is Cringe Master C, catching you on the flip side.